Okay, so in this last part, I just want to show you some very recent results on designs. So we're going to look at designs on some very well-known graphs and see if we can understand what they are and whether they are connected to other things that are known already, okay? So I will spend most of my time on the hypercube graph. So let's look at designs on the hypercube graph. Okay, so I'm going to call this graph HN2. So let's look at just the binary hypercube. Okay, so this is the name of the graph. So the vertex set is the set of all 0, 1 vectors of length n. Okay, so for example, you can think of, let's just have an example in the background. So I want to take all 0, 1 vectors of length n. Let's do it for n equal to 3. So I'm taking all 0, 1 vectors of length 3. Right? So these are 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, and then 0, 1, 1, and this one is 1, 0, 1. Okay. So these are the 0, 1 vectors of length 3. This is n equal to 3. And of course, if you convexify it, you get the hypercube. But I only want the graph of it. Okay, so I just only want the one skeleton of this cube. So the edges of the cube is what we're taking. Okay, so the cardinality of the set, of course, is 2 to the n. So we have a lot of things. And then the edges are basically defined by Hamming distance. Okay, so let me just define what this is. So the distance, the Hamming distance of 2 points x and y. So if I pick an x and y in my vertex set, then the Hamming distance between them is just the number of places in which they differ. Okay, so the number of coordinates in which they differ. So number of coordinates in which x and y differ. That's the Hamming distance. So the edge set of this graph is basically the set of all x, y, such that the Hamming distance between the two is 1. Okay? So we connect every two 0, 1 vectors that differ in exactly one coordinate. Okay? So let's quickly check. These two things differ in exactly the first position, so they're connected by an edge. This and this differ in exactly one position, right, the middle position, so they are connected by an edge. This and this differ in one position, and so on, okay? So that's a rule for connecting the edges if you don't want to think of it as coming from the cube, okay? So this is the rule for connecting edges. So edges, I will often just write them just stuck like this, x, y. It means that x is a vertex and y is a vertex, and that is an edge, okay? All right, great. So this is the Hamming Hamming graph, the binary Hamming graph, because here, yeah, hypercube. But I only want the graph, and I'm putting the 2 here because we are working with 2 letters, right? 0 and 1 are the things. In general, you could work with q letters. You could take 0, 1, 2, 3 up to q, or q minus 1, and then look at all length n strings on those, and that'll give you h, n, q, okay? And the rule of making the graph is the same. You connect 2 things if they have, if their Hamming distance is 1, okay? But I won't talk about those general Hamming graphs at all. I will tell you that what the results are, but I'm not going to actually focus on them. Okay. All right, so we'd like to understand designs on this, okay? So for that, I first need to look at the Laplacian. I need to see what are the eigenvectors, what are the eigenvalues, and so on. And this is very beautiful. This is actually a Cayley graph, if you know what that means. It comes from a group, right? The group over here is this set is also z bar 2z to the n, or z2 to the n, whichever way you want to think about it. This is an abelian group. And then I'm making a graph on it. If you know what Cayley graphs are, then the connection set is just all the unit vectors. This is a Cayley graph. Okay, so for Cayley graph, we know all kinds of things. But if you don't know it, don't worry. So let's just look at what we know about the structure, the eigenstructure of the Laplacian. So I'm going to remove this Hamming distance definition, and then let's actually put down what we know about the Laplacian. So the Laplacian is, of course, a vector that a matrix that lives in 2 to the n by 2 to the n space, right? There are that many vertices. And its eigenvalues are basically controlled by the various Hamming weights inside this cube, okay? So if you look at all the different vertices, you see there are only n plus 1 different Hamming weights. Hamming weight means the number of ones in a 0-1 string, okay? That's the Hamming weight. So this one, for example, has Hamming weight 0. And these, all the unit vectors have Hamming weight 1. These guys have Hamming weight 2. This one has Hamming weight 3. So in general, there are n plus 1 Hamming weights, distinct Hamming weights. And that's what controls the eigenvalues. So the eigenvalues are in general 0 to 4 up to 2n, okay? So the general formula is 2i, where I is a Hamming weight. These are the eigenvalues of the Laplacian. Okay, so we know they have to be non-negative, they indeed are, and there is exactly n plus 1 of them, n plus 1 of them. Okay, so this means that somehow the Hamming slices of the cube are controlling the eigenspaces, right? So 0 weight comes with one eigenspace, Hamming weight 1 gives you another eigenspace, and so on. Good? And then we know some more things. We know that the multiplicity of this eigenvalue, 2i, is exactly n choose I. Okay? That's also the number of 0-1 strings with I-1s. So there's a lot of, like, the universe smiles on the Hamming cube. Okay? Lots of nice things happen for the Hamming cube. This is true. And the eigenbasis that goes with the eigenvalue 2i is generated like this. So what you do is, so I'm going to give you the recipe for writing this down. If you know representation theory, these are the characters of z2 to the n. If you don't know representation theory, here's the formula. So what you do is the following. So let's pick a y inside 0, 1, 0, 1 to the n. Okay, so pick a y. And let's suppose that its Hamming weight is I. Okay, this is Hamming weight when I write 2 bars like that. And then I'm going to, from this y, I'm going to define a vector, which I'm going to call chi y, because it's a character. And this is going to be something that lives in 2 to the n space. And the formula is all, so this thing has a coordinate for every x in 0, 1 to the n, right? Its length is 2 to the n. So its coordinates are going to be indexed by all the white dots here, right? So I just need to tell you what sits in the x position of this chi y, where x is a 0, 1 vector. Okay? So that's what I'm going to tell you. So the formula is that chi y, if you look at what happens to it in coordinate x, okay, x is a 0, 1 vector, and y is also a 0, 1 vector, but I'm fixing the y of Hamming weight I, and this character or this vector is defined, this value is defined to be minus 1 to the x transpose y. Okay? So let me do an example just to make this very clear. Good? That's the formula for how you write this chi y. And all the chi y's of Hamming weight I are going to span this eigenspace. That's the claim. Okay? So let's do an example. So I'm going to do the 3-dimensional example. So I'm going to collect all the eigenvectors in this table. Right? So I know there are 4 different Hamming weights, right? So there is 0 Hamming weight 1, Hamming weight 2, Hamming weight 3. So I expect 4 eigenspaces. And their multiplicities are going to be 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Okay? So it's going to be 1, 3, 3, 1. Okay? That's going to be the multiplicity. So this one comes with the first eigenvalue. Let's put the eigenvalue here. This is eigenvalue 0. Then I will have 3 rows that comes with eigenvalue 2. Okay? Then I will have 3 rows that come with eigenvalue 4, and then I will have 1 row that comes with eigenvalue 6, right? That's exactly and 3 choose I, right? So those are the eigenvalues. And now what we have to do is I'm going to index let's index the rows by the various 0, 1 vectors of different Hamming weights. Okay, that one is Hamming weight 0. Then for Hamming weight 1, I have 3 of them. Okay, then for Hamming weight 2, I have 3 of them. And for Hamming weight 3, I have 1, right? So these are the Y's. I'm going to pick, I'm choosing everything of Hamming weight something. So and those are the Y's, okay? So in here, these are the Y's. And so for each Y, I'm going to write down a vector which is called chi Y, okay? Let's do it. All right. So for the first one, what do I have to do? So chi of 0, 0, 0 in position X is going to be -1 to the 0, 0, 0 transpose X. Okay, X is again a 0, 1 vector. So that's always going to be 1, right? Because X is, so you have to vary X over all 0, 1 vectors. You have to do this, okay? So no matter what X is, it's making a dot product with 0, 0, 0. So the top exponent is always 0, -1 to the 0 is 1, okay? So this top one is 1. So let me also put the Hamming, these guys here. Okay, so 0, 1, 0. Yeah, I'm ordering them the same way. You don't have to, but we can order them the same way. My students always like to order this in binary expansion. I'm like, why? But that's what they do. Okay, so my spacing was not so great, but that's what it is, okay? Actually, let's make the spacing better. I don't like this. Okay, so the first, okay, make it a little better. Okay, so let's do this. Okay, so this is 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. Okay, so the first row is all 1s, we agree? Okay? All right, so it's not symmetric or anything like that, okay? So I have to really work. Okay, what happens in the first column though?
Because of your choice.
Oh, because I chose it like that, yeah, true. Yes, so in this first column, I should also get 1s. Everybody okay with that? Because the exponent is still, you know, X is now playing the role of, X is now 0, 0, 0, and Y is varying. So I still get 1s, okay? Those are okay. So let's calculate one more. Maybe we'll calculate this row. So this one is going to be chi of 1, 0, 0. And then the formula is going to be -1 to the dot product of 1, 0, 0 with X. So it's just X1, right? That's all we need to do. Okay, so -1 to the X1. So here is, yeah. So this one and this one, the X1 is 1. So this is going to be -1, okay? This and this is going to be 1, right? Can you check? So the dot product of this vector and this vector is 0. So I have -1 to the 0. This is also 0. So this is also 1. This is going to be -1, right? The dot product is 1. So it's -1. Again, it's -1, then a 1, and then a -1. Is that okay? All right. Just look at it for a moment. Make sure you believe it. That's the formula. Okay. So essentially, we're looking at the intersection of, yeah, you see the pattern, hopefully. So all the eigenvectors are going to be plus or minus 1 vectors, and that's the formula for calculating them is exactly this. Yeah, exactly. They're orthogonal by group orthogonality of characters, or, yeah, fine, yeah. So you'll have to, I mean, if you did not know any representation theory, you may have to work a little harder to know that these are orthogonal, but they're orthogonal for free, okay? Good. All right. So that's what these eigenvectors are. Okay, so we got all the eigenvectors, we got everything. So the question I want to ask is, what are the graphical designs? Designs of this graph that can average eigenspaces in the order, in this order, from top to bottom, okay? So this is, we call this Laplacian order. So as eigenvalues increase, I want to average more and more eigenvectors, okay? We call this Laplacian order. So what are the graphical designs of Hn2 that average oh, I call this E2i. Let me just call this EI. It's just indexed by Hamming weight, okay? So the different eigenspaces are basically, this one is E0, this one from here to here is E1, this one is E2, and this one is E3. So I am indexing them by Hamming weight. So what I want to average is E0, which is for free, then E1, all the way up to some ET, okay? So I want to go down in exactly this order. I'm telling you the order in which I want to average. Is that okay? This is for the general cube. We're asking what are the designs that can average the first T eigenvectors in this order, in increasing eigenvalue order, okay? All right, so that's that. And we discussed in the previous lecture, but also we discussed in the class that no proper subset can average everything. So, and also we discussed that the all ones is averaged by everything. So we always leave out the top row, right? We don't really care about the top row. Okay, so let me show you some examples. So the first example I want to do is, let me call this D1. This is a design. It consists of 0, 0, 0, and 1, 1, 1 in the three-dimensional cube. So let's draw the picture again. So these are two antipodal points. Okay, so it's this one and this one. This is D1. Okay, so I claim that D1 can average it can average E1. This is a E1. So let me give a name to this. So let's call such designs D T, okay? D with the set T. That means that it'll average all eigenspaces indexed by everything in that set. E1, E2, E3, up to ET, okay? So this is a design that can average the first eigenspace. So this is a design that can average the first eigenspace. We didn't put down the whole thing. If you had, then you will see that the first one and the last one. So this last one here, let's calculate this. Yeah, this is minus, minus. So now you see that if I just take this vertex and this vertex, they will just add up to 0, right? So if you take these two antipodal points and you sum them, the weights are uniform, you get 0, 0, 0, okay? So that is clearly a design that can average the first eigenspace. Okay, here's another one. So D2, I want to take it to be something else. So I can also, this one I want to take it to be 0, 0, 0, and 0, 1, 1, and also 1, 0, 1, and 1, 1, 0, okay? So I'm going to draw it into the same picture with a different color. So this is again this vertex is in there, 0, 0. But now I take this vertex and that vertex and that vertex. This is D2. Okay? And I claim this will also average the first eigenspace. In fact, it will average the first and second eigenspace. So this is a D2 design. It'll average the first one as well as the second one. By first one, I mean E1, okay? So E1 doesn't, it leaves out the all ones. So it averages E1 and E2. So to fully see that, we would have had to fill out this whole matrix, and then you will see that if you add those columns corresponding to those four numbers, those four vertices, then you will get exactly 0, okay? All right, so these are vertices of the graph, okay? This is very confusing, but remember that these are vertices of the graph. So when I write that down, I'm just picking some vertices of the graph, okay? That'll also average, okay? So now notice something very nice is happening with these sets. This one will not average the second eigenspace, but this can average the first and the second eigenspace, okay? But now I want to write this second one in a slightly different way. I'm just going to put them one below the other like this.
This average, this creates 0 in 6 coordinates.
Yes, 6 coordinates. So it'll average those 6-dimensional columns. If you add up what you see under 0, 0, and so on, if you add up those columns, you get 0, 0.
So this is strictly less than 6.
Yes, it's strictly less than 6, exactly. Okay, but let's just look at this example like this. Okay, I just wrote them one below the other like that. And now pick, so note this 2, this is a 2. Okay, this is a 2. So pick 2 columns arbitrarily, okay? So this is my human randomization. 2 columns arbitrarily. Pick any 2 columns. Let's pick those 2. What do you notice? Do you notice something nice in the rows? You see all the vertices of the 2-dimensional hypercube, 2-dimensional Boolean cube, appear equal number of times, right? They appear once, all of them. Okay, what happens if you picked another 2 columns, like these 2? You also see all the vertices of the 2-dimensional cube appear equal number of times. And then if you pick the first column and the third column, also the same, okay? So these kinds of arrays of 0, 1 strings are called orthogonal arrays, okay? So arrays that have this property. So let me actually write the definition. So the definition of an orthogonal array is the following. So an orthogonal array so this is very dear to the hearts of coding theorists. I will write it like this, orthogonal array, and it has 3 parameters, okay? So the n and the 2 come from the cube that we are working with, okay? 2 tells me that we are working in the alphabet 0, 1 binary. N means that we are looking at strings of length n, okay? So these 2 we've kind of fixed, and this t is the extra number that we have. So this is a binary string. This is a binary, is a collection. It's a collection of 0, 1 vectors, let's say. So in our example, we only need 0, 1 vectors such that, actually let me write it more mathematically. So this is a set D that lives inside Z mod 2Z to the n, right? It's a collection of n length strings such that any subset of t coordinates, contains every element of 0, 1 to the t equal number of times. This is an orthogonal array, okay? So I have a collection of 0, 1 strings of length n, so that if you restrict to any t coordinates, you will see all the vertices of the t cube appear equal number of times. In this example, it appeared just once. All the vertices of the 2 cube appeared once. But in general, it can appear 3 times or 4 times or whatever number of times, but they're equal.
Even in this example, if you just take 1 coordinate, the number of zeros and
that's right. So if you take 1 coordinate, then it's true that there are 2 zeros and 2 ones. Those are the vertices of the one-dimensional cube.
So if it is OAT and 2, is it also OAT minus 1 and 2?
Yeah, it must be, right?
Therefore, by derivative.
Exactly. So if it works for t, it also works for any number less than t. Because if it fails for less than t, then it cannot build up to become okay for t. Okay? So this is actually, this t is called the strength of the orthogonal array. So this array we just wrote down here, it's both a 2 strength array and a 1 strength array. If it's 2 strength, it's automatically 1 strength.
So I think of this as rows. I mean, the subset is what? The rows or the column?
The rows. The rows are the subsets. And then I have to write them one below the other. So it's a subset of z mod 2z to the n, so that when you write them one below the other and restrict to any t coordinates, you see all the elements of 0, 1 to the t appear an equal number of times. Okay? These are called orthogonal arrays. They're very, very, very symmetric, right? So they're saying that they're equally distributed on the vertices of the lower dimensional cube, this object. Okay. So that's what it is. Yeah, so this thing that Apurva just asked, I had noted here. So you should note that if you're an orthogonal array of strength t, then you're also orthogonal array of strength t minus 1, t minus 2, all the way down. Okay? So we don't have to check that part. Okay, great. So let me write down the first theorem, which I will not prove, and then we'll go on. Okay? So theorem. Where to write it? Maybe here. Okay, so theorem. This is a theorem with Zawad Chowdhury and Stefan and me, Steinerberg and me. It's very new. It's 25. Okay. So this theorem says that d in 0, 1 to the n averages E0, E1 up to Et. So this is a T design. If and only if D is an orthogonal array, is an orthogonal array of strength T, parameters n and 2. Okay? So the designs are exactly these orthogonal arrays. If you want to average T eigenspaces, the various designs you can pick are exactly the strength T orthogonal arrays. Is that okay? Okay, I won't prove this because the proof is hard. Okay, it takes many pages and drove me crazy, but it is correct. And it also works if you replace this 2 here or HN2 with HNQ. Okay, so you can do strings with alphabet 0, 1, 2, 3 up to Q minus 1. You can take all n length strings where you're allowed to put any number between 0 and Q minus 1, construct the graph. And then you will have to just change this 2 to Q. Okay? So this is a very general theorem, and the proof is, I don't know, at least the way we proved it is through Radon transforms and stuff like that. That's why I'm saying the proof is hard. Okay? Okay, let's ignore this, but I'll show you some other stuff which is, I think, much easier to discuss. Everybody okay with this? This is exactly orthogonal arrays. Okay? So as I said, orthogonal arrays are really dear to the hearts of coding theorists. They really love this. So if you look in the books of that fat book of McWilliam Sloan on coding theory, for example, these things appear a lot. Okay, they like these. These are codes, right? These are like nice codes. I don't know if this is actually a code, but it's codes are just subsets of vertices of the cube that can correct errors. So there's a big book on error correcting codes that Neil Sloan and McWilliams wrote, and you'll see these all over the place. Okay. Fine, so that is the first result. So we understand the designs, that's the bottom line, okay? So now let me tell you a second result, which I can tell you a little bit about. So, maybe some of you know of the Hadamard conjecture, which is open. It's an open conjecture. So this question that we are asking is related to the Hadamard conjecture, okay? So let me actually explain what the Hadamard conjecture is. So just slightly switching gears. So definition. So we'll say that a matrix M in -1, 1 to the n minus n. Okay, so this is a matrix of size n by n filled with plus ones and minus ones. So this matrix is Hadamard if its rows are mutually orthogonal. Pairwise orthogonal. Okay, so let's see a quick example to agree that it exists. These exist. Okay, so here's a 4 by 4 example. So my first row is all ones. Next row is this. Okay, everybody okay? Those two are mutually orthogonal, no problem. Then the next one is this. Now you have to work a little harder to check that the third is orthogonal to the second. Okay, works. And then the next one is this. Okay, that's a 4 by 4 matrix. That's Hadamard. It's filled with plus ones, minus ones, pairwise orthogonal in the rows. It's even symmetric. It's nice. Okay.
This is the H22.
This is the what?
Isn't this H22?
X.
The
S22.
matrix you do for H32.
H32. Yeah. Okay. Maybe. Yeah. Maybe. Okay. Okay. So what do we know? Okay. So what we know is that. So we know that n by n Hadamard matrices exist for n equal to 1 and 2. Okay. And they also exist, or it has to be some multiple of 4. This is known. Okay. So if you're a Hadamard matrix, the n has to be 1, 2, or a multiple of 4. Okay. And the Hadamard conjecture is that it exists for every 4k. So the conjecture, which has been open for 100 years, is that there exists Hadamard of size 4k by 4k for every k from 1 to onwards.
What is it? Well, that seems to contradict the first line.
No. What?
Yeah, so you want to say Hadamard will not exist.
No, I want to say, no. The conjecture, so we know that if it exists, its size has to be divisible by 4. But we don't know if it exists for every value of 4k.
So it's the opposite. It's like
Okay, where did I go wrong? Oh, so let me say can exist. Only for. Okay, thank you. Okay, if it exists, it has to be the 1 or 2, the size, or it has to be a multiple of 4. This is known. Okay, that the size has to be divisible by 4. And the Hadamard conjecture, which I said is about 100 years old, is saying that there is a Hadamard matrix of size 4k by 4k for every k. Okay, another open problem for our Gyan students. Okay, so this is the Hadamard conjecture. Okay, and I don't know, people work on this. For example, it was shown for n equals 428 in 2004. Okay, there's a paper that shows there's one for 428, but we don't know if it exists for every value of 4k. Okay, this doesn't know. Okay, so what I'm going to show you is that finding designs on the hypercube that average E1 and E2, just the first two, the existence of those designs is tied to the Hadamard conjecture in a certain way. Okay, so let me write down what the conjecture is. We know they exist. For us, they exist. Okay, but I'm going to say something a little bit more specific. Now we can erase this. So, yeah, okay. So basically, once we understand that designs are orthogonal arrays, then you can use all kinds of properties of orthogonal arrays you can use all kinds of things known about orthogonal arrays to say something about designs. Okay, so that's the idea. So here's the theorem. theorem says that D averages, so D is my design, so D averages E1 and E2, the HN2. We're still in HN2, okay? Okay, so the graph is still HN2, so this averages this and this, implies a couple of different things. The first thing is so that 4 divides the size of D. That's the first thing. That is easy, we'll see. More hard is that the size of D is bigger than N. Okay, so this also we can prove. But then this is the piece that I want to really focus on. So when N is equal to 4L minus 1, okay, then there exists a design of size 4L, if and only if there exists a 4L by 4L Hadamard matrix. Okay, that's the claim. So we know there are designs that average E1 and E2. That's not a problem, okay? The claim is about the size of such a design. So if I take N to be 4L minus L, then I'm saying there's a design of size 4L, this particular size, if and only if you can construct a 4L by 4L Hadamard matrix. Okay, so this is a pretty small size that we're looking at. Oh, it's not a small size necessarily, but it's just a statement that connects the existence of designs that average E1 and E2 to the existence of a Hadamard matrix. Okay.
N can be arbitrarily long. So N does not have to have any relation to L, right?
No, but it has to be like this. It has to be like this, okay? Okay, so I'm going to show you a little bit of this proof just to show you how this works, okay? So first of all, do you agree that 4 has to divide the size of the design? Let's agree on that first.
So the first statement is not different only. That's just implied.
It's just all implication, okay? So why is that the case? So remember, the design averages E1 and E2, right? So that means it's a strength 2 orthogonal array. That means if you look at any 2 columns, you should see all the vertices of the 2-dimensional cube appear an equal number of times. The 2-dimensional cube has 4 vertices. So whatever the size of the design is, it has to be divisible by 4, right? 0, 0 has to appear some number of times, 1, 1 has to appear some number of times, and there are 4 of those. So that's why 4 divides the size of D. Okay, that one is easy. D bigger than N, let's ignore, okay? And this one, I'm just going to show you one direction. I'm going to show you how you take a Hadamard matrix and convert it into a design. Okay, so we'll do one direction. That's the easy direction. So we'll do that. Okay, so let's start with an H. Let's not call it H. M. Hadamard of size 4L by 4L. So from this, I'm going to construct for you a design that can average E1 and E2. Okay, that's the idea. Okay, so let's work with, we had that example there, right? So let's think of, just keep this in your head as an example of a Hadamard matrix, okay? So this one had the property that all ones was already one of the rows, okay? Now, if all ones is not one of the rows, can you negate columns as needed so that all ones appears as one of the rows without destroying the mutual pairwise orthogonality of the rows? So let's think. So suppose I take, okay, here we already had all ones, but suppose I make everything here negative, okay? I just change the sign of that whole column. I claim it doesn't mess with the orthogonality of the rows, right? Because when you make a dot product, you're multiplying these two. This is a plus plus. If I turn it to minus minus, that's also okay. Still going to contribute a plus 1. So I can independently negate the columns until an all ones appears on top. Everybody okay with this? In this example, all ones is already there, so I don't have to do anything. But this is step 1, okay? So step 1 is to negate columns until the all ones is a row of M, okay? And then we'll work with this M. It's a new M, but I'm still calling it M. This is step 1. Everybody okay? You guys okay? Yeah? Okay. All right, so this is the first step. So let's assume we have all ones in the top row. And now what I want to do is let's work with this matrix since it's already sitting here. So my matrix now looks like this one, okay? It has an all ones row and we can put it in the top if you want, it doesn't matter. So let's put it in the top. Let me erase this and draw this again. So this was a 1, this was a 1 and a -1 and a -1, okay? So this is my M, okay? Now I'm going to just cut off this row, this all ones row. Okay, fine, okay? So cut off the row and now take this matrix and transpose it, okay? So let's transpose this matrix. So this is the transpose of what is left. So transpose means I have 1, 1, -1, -1. This is the second row. And then the third row is this. And the fourth row is this. No. 1, -1, -1, 1. Okay? So this is transpose. Okay, so I cut off the top row and I transposed what's left. Do you have a question? Sure. Happy to answer. You good? Okay. Everybody okay so far? Okay, so we do that. And now we're going to make a linear transformation that sends all the, let's do a linear transformation that sends 1 to 0 and -1 to 1. Yeah, then you get that, exactly. So then what do we have? So in this example, we are in good shape, but we'll argue in general, 0, 0. All the 1s become 0s and the -1s become 1. Okay, this is a linear transformation. This is okay too. And I claim that whatever you get here is going to be orthogonal array of strength 2. So the claim is that this guy is an orthogonal array of strength 2, and then there's n2, okay? But the strength is what we need to worry about. So what we need to show is that if I pick 2 columns, which in this case we already verified, but if I pick 2 columns, then the number of times 0, 0 appears is the same as the number of times 1, 1 appears, is the same number of times 1, 0 and 0, 1. Good? Okay, so this is the last bit. So let's look at how many, so in general, okay, in this example it's clear, but in general, if you look at a pair like this, okay, so if I look at a 0, 0 and a 1, 1, okay, then in the original, what was it? In the original, this was a, yeah, so the zeros came from 1, and this is a -1, -1. Okay, so this contributed, yeah, so what do I want to say here? So I want to say that this contributes a +1, okay, all right, I'm going to get confused here.
Because there you are looking at rows, now you are looking at columns.
Yeah, now I'm looking at column. Oh yeah.
So then this will give you a 2.
This will give me a 2. So this will contribute, so this, no, but I want to take the, basically I want to take the dot product of the rows, okay?
Here, no, here you want columns.
Yeah, I'm looking at a column, and I want to argue that the number of times this pair appears is going to be the same as the number of times this pair appears. That's basically what I want to argue, okay?
Yeah,
so
that's what I'm saying. So if you look at now, because you transpose, now you're looking at column orthogonality of
yeah, orthogonality of columns, exactly.
So these two will give you 2.
This will give you a 2, right? This will give you 1 time 1, and then -1 time -1, which is also a 1. Yeah. Okay, so this will give me a 2. This will give me +2, okay?
Each one will give you 1.
Exactly.
And here each one will give you -1.
And this one will give us, this is a 1 -1, and a minus 1, 1, right? This will give me a minus 2, right? So when I do the orthogonality of the rows, you see that the number of times 0, 0 and 1, 1 appears has to be the same as the number of times 1, 0 and 0, 1 appears. They have to be tied because the rows are orthogonal, okay? So that is the end of the argument. So we argue that the number of times this pair appears is the same as the number of times this pair appears, but within each pair they appear equal number of times. So altogether this becomes an orthogonal array of size 2, okay? So from a Hadamard matrix, we have constructed an orthogonal array of size 2. And then the reverse proof also works. If you have an orthogonal, then you use which theorem?
You want to design.
Yeah, that's right. So we use the fact that designs are orthogonal arrays, and then orthogonal arrays will give you Hadamard matrices. Okay, so this is one proof. Okay, so in a way, so this is just saying that the complexity of finding Hadamard matrices is tied up in the complexity of these designs as well. Okay, so that was the second result. Let me show you 2 more results of the hypercube, and then depending on time, we either stop or I tell you something more. Okay, so
size of E1 and E2 together is exactly n plus 1.
Correct.
So this is a case where it would be tight.
Yeah, this is tight.
But sometimes it doesn't exist. This is because you are not allowing weights, is it? I mean, you mentioned the theorem without weights. That's not
Correct.
always
That's right. So in general, we are not guaranteed uniformly weighted designs. Okay. But in this example, they exist by this recent result of Kuperberg, Lovett, and Peled.
But you do say that sometimes it doesn't take. Oh, okay. We don't know whether Hadamard matrices.
Yeah, we don't know if Hadamards exist. Okay. And probabilistically they exist according to Kuperberg, etc. So they showed that, okay, they didn't show that there are designs of this size particularly, but they showed that there are designs of size at most this. Okay, so that's what they proved. E1, E2. Sorry? Which one are you talking about, Apurva? So I want to average.
Yeah, size is n plus 1.
No, you're right. Yeah, sorry, I'm wrong. This is n plus n choose 1. No, these are the sizes. Yeah. E0, yeah, sorry, I got confused. So it's really n plus n choose 2. That is the big size, and we're actually getting something smaller size, right? Yeah, so we're actually getting something of much smaller size, and we're saying that can exist only if a Hadamard exists. Okay? Yes, thank you. Yeah. All right, so let me show you 2 more results. One with changing the order of the Laplacian, and 2 with, well, I'll show you 2 more things. Yeah?
General question.
Yeah.
All the hypercube graph, the tetrahedron chopping off graph, these are very symmetric.
Yeah.
If you have one design, then you can symmetrize.
Yeah, it's you can push it around with the automorphism group of the graph, correct?
Is there some more philosophical statement about existence of designs versus existence of symmetries?
All I know personally is that you can, if you have a design, you can make the group act, you'll get all designs. But we don't know too much about how to use the symmetry of the graph to compute designs. There's actually an open question too. If I know the graph is highly symmetric, can I exploit it to compute the design? We should be able to, but I don't quite know how to do the symmetry reduction for that, okay? Okay, so let me say one more thing. I'll just say one result, just talk about it, okay? So in Laplacian order, we went from smallest eigenvalue to the biggest, and we were averaging 1 by 1 by 1, right? But if you go the other way, if you average the biggest eigenspace, then the next, then the next, then the next, then what you get is just small subcubes, okay? So let me show you that picture. I won't write the result. So for example, if we had the 3-dimensional cube, if I go in reverse Laplacian order, then you end up just picking up a subcube of the big cube, and that is the design, okay? And how do you know which one? So if I want to average like t of them, I guess, then I want to fix like t coordinates and look at the subcube that I get, okay? So they're like very different in philosophy, right? This is like crouching in one corner of the cube. It's all like together, this design. Whereas the orthogonal array is like nicely spread all over the place because it has to have this uniform distribution on the vertices of 0, 1 to the n, right? Every t coordinates has to be uniformly distributed on the vertices of 0, 1 to the n. So you get something very, very different looking if you try to average from the bottom up, okay? You may or may not want to do it, but it's kind of interesting that that's what it is, okay? One other result that may be interesting for some people, since we talked about the walk matrix and random walks, is that, let me write that result. This might be interesting. So if I have a regular graph again, because that's the only one that I want to do random walk in. So let's take G to be deregular. And let's look at the walk matrix. This is the walk matrix. And remember that this matrix has spectrum between plus 1 and minus 1. This is where the spectrum lies, right? So 0 is in there. 0 is sometimes an eigenvalue, sometimes not an eigenvalue. So let's take the case where it is an eigenvalue, okay? So let's suppose that 0 is an eigenvalue. 0 is one of the lambdas of this matrix, okay? So this is an eigenvalue. So, and this is just a normalization. You can actually get rid of this. But then, this is the result. If a design averages all eigenspaces except the eigenspace of 0. So, all EI except the eigenspace of lambda equal to 0. Let me write it like this, okay? So, this is not E0. I've changed the matrix, so it's a different spectrum, and this one is kind of the middle eigenvalue. So I don't want to average this eigenspace, but I want to average everything else. This is an example of an extremal design. We're leaving out one eigenspace, but averaging everything else, okay? So if this happens, then it turns out that every point, every vertex, every V in V is adjacent to M vertices in the design, okay? So the one neighborhood of the design is some number and some positive number to some M vertices, okay? So what is this saying, right? This is saying that if you take the design, so maybe in red I have my design. Here is my design sitting somewhere. And then we also have all the other vertices of the graph. Let's call them, make them green. These are the other vertices of the graph. So it's saying that if this pink is a design that can average everything except the middle one, then all the pink vertices, all the green vertices connect to something pink. Something pink. Gosh. I'm really messing this up. Okay, so all the greens connect to something pink. Yeah, same number of pink. What? No. Okay, yeah, so I only want V in V minus D. Yeah, V in V minus D. So all the other vertices.
So M equals 1 means you're talking about a domination set.
Yeah. So it's like saying the one neighborhood of the design is everything. So that's like you can quickly get to everything. And the argument is a random walk argument, basically, okay? So what you do is, so the idea is the following. If you have such a design that can average everything except the eigenspace of 0, then it means that it lies in the span of the all ones eigenvector and the eigenvector and some eigenvector of 0. Do you agree with that? So let me write it. So I take the design and I look at its characteristic vector. okay? So this means there's a 1 in position I if the element is in the design, and 0 if the element is not in the design. This is the characteristic vector of, maybe we call it chi-D. That's what we were calling it in the Gyan course. Okay, so this is the characteristic vector of the design. Okay, so it has length equal to the number of vertices. I put a 1 if the design vertex is, if the vertex is in the design, and 0 otherwise, okay? So this thing can average, so this is really like a zeros and ones, right? It can average all the eigenspaces except E0 and the very first one, the 1, 1, 1, 1, 1, okay? That means when you dot it with all the other eigenspaces, you get 0. That means this must lie in the span of the all ones plus something in the eigenspace of this one, right? Because all the other dot products are 0, so this must really lie in the span of these, right? Remember, the dot product of this with any eigenvector is the coordinate, because this is an orthonormal eigenspaces, so you get something like this, okay? Now, so what happens if you hit this vector with AD? So let's try to multiply this with the walk matrix. So if I try to multiply this with the walk matrix, so think of this as the measure that I'm sitting on, and I run one step of the random walk, okay? That means I multiply with 1 over dA. So then here I will get C times over D, and then A times 1. Yeah, so A times 1 is 1 times D, right? So this piece is C times 1, right? And what happens to this piece? So I will get 1 over dA times F, but F is in this eigenspace, the eigenspace of 0, so this goes away, okay? So this becomes C times 1. That means in one step, I equidistribute. I get to the uniform distribution in a single step if I start on this measure, the measure that's supported on the design, okay? And now this means what? This means that in one step, all the greens got picked up, okay? And how does the random walk move, right? The pink guy just distributes all its measure equally among its neighbors, right? So the green got a whole bunch, so green got connected to a bunch of pinks, but because of the regularity and so on, the number of, so you can then argue that the number of neighbors of each green is the same in the different pinks, okay? So that's the argument. So it's a random walk argument that if you will immediately equidistribute, and therefore the pink has to be connected to everything, including itself. Okay, so this is a one neighborhood. So this was an observation in one of Stefan's original papers that these designs are very nicely distributed. They look like the one neighborhood of a design is the whole graph, and they prove some results about it. But in this case, you see it explicitly. Okay, in this design, this is a very fast get to everything. Okay, so that's all I want to say about the hypercube. Let me show you one very quick result, which is nothing to do with the hypercube, okay, which is another class that we did. And then I will say a word about the symmetric group since Apurva is here. And that is a little bit messy, and we don't know a lot. So open question will arise immediately, okay? So there is a class of graphs called Misalskians. Have you heard of it? Misalskians. Let me write it, right? Yeah, Mycielskian. Okay, this is actually a construction on a graph. Okay, so this is due to Jan Misalski, and it's from 1955. And what he was trying to disprove is that if you have a triangle-free graph and you keep on increasing vertices, is it true that the chromatic number doesn't go up? Okay, and this construction shows that chromatic number can go up even if you remain triangle-free. Okay, so I'm going to give you the definition with an example. So let's start with a pentagon. This is my original graph. Okay, so this is G. Okay, now the Misalskian of this G is got by duplicating all the vertices. So we duplicate. Okay, so we have another, so we have 2n vertices now. But then you also put a central vertex in, and we'll call this U. Okay, this is central. So the first step is you connect all the pink vertices to the central vertex. That's okay? All right. Now you have to do something interesting. So you pick an edge. So if this is I, and this is J, and this is the clone of I, and this is the clone of J, okay? So IJ was an edge. So what you're going to do is you're going to make this cross. You go from I to J prime, and I prime to J. You make the cross like that. For every edge, exactly. So for this edge, I got to do this. For this edge, I got to do this. And for that edge, I got to do this. And for this edge, I got to do this. Okay, that's the missile skin of the original graph. Good? So in this example, it's nice to work with the adjacency matrix. So the adjacency matrix of the missile skin of G, this is my notation for the missile skin. So what we just constructed is the missile skin of G. This has this nice form, okay? So this looks like A, the adjacency matrix of the original graph, then another A, and then a 0. This is right? N vertices, and then one vertex. So that's the size. And then A, and 0, and all ones, and then 0, and all ones transpose, and 0. This is how the adjacency of the missile skin looks. It's very nice, okay? And there's a nice relationship between the eigenvectors of G and the eigenvectors of the missile skin and so on, if you work with the adjacency. The Laplacian is kind of a mess. So this is an example where you want to choose another matrix to do designs. And then the theorem is that this blue vertex can average all eigenvectors except 3. Okay, so this thing has 2n plus 1 eigenvectors. So the U vertex, U, this can average 2n minus 1 eigenvectors. That's the result, okay? So this central vertex is a super good sample on this graph, okay? It carries all the information of this graph in a way, right? It's a super good sample. And if you want to be a little bit more greedy and you want to like average one more eigenvector, you're out of luck. You need the whole graph. Okay? So you have to kind of stop being greedy here. Okay? U is good. It'll average 2n minus 1 eigenvectors. But even one more eigenvector requires the entire graph. So I won't write that. Is that okay?
So 2n minus 2, you said 3 you cannot have.
So the total number of eigenvectors is 2n plus 1. 2n minus 2 maybe? I don't know. What did I write here? 2n minus 2. Yeah, it cannot average 3. So it's 2n minus 2. Thank you. So it leaves out 3 eigenvectors. And if you want to do one more, then you need the whole thing. Okay, so it jumps from 1 to n, 2n plus 1. Okay, so that's right. Okay. So let me finish by just telling you the story for Sn, again, in honor of Apurva. So Sn, okay, so in this paper we look at, so orthogonal arrays are like very well studied combinatorial objects, and the point of the paper was to show that they are graphical designs, and therefore you can bring tools from spectral graph theory to study orthogonal arrays, okay? They come kind of naturally like this. Another class of combinatorial objects that people love are called combinatorial block designs. Whatever they are, we won't go there. But we also show that those are graphical designs on something called the Johnson graph. Okay, never mind. But then for people who like permutations, there is a thing called T-wise permutations. Okay, so what that means is it's a collection of permutations inside Sn. So it's a subset of Sn. Okay, maybe I shouldn't call it S. So let's call it, I don't know, T. Okay, it's a collection of permutations that have the property that if you pick I1, I2, I3 up to IT, and you pick J1, J2, J3 up to JT, then the number of permutations that send I1 to J1, I2 to J2, IT to JT is the same. Okay? So I have a collection of permutations, and then you are allowed to pick any T tuple and another T tuple. Okay? I1 through IT, J1 through JT. And then I look at which permutations in my collection will send I1 to J1, IT to J2, I3 to J3. I get some number. Then I pick another I1 through IT and J1 through JT. Count again. How many permutations will send I1 to J1, I2 to J2? You should get the same number as before.
This number can be 0.
Can be 0. Okay.
It's for a fixed T or at one until every number until T?
No, fixed T. Fixed T, yeah. So what I mean, so this is a T-wise permutation, little t wise, a set of permutations we should call it, set of permutations if for every I1 through IT, J1 through JT, the number of pi in T such that pi I1, pi IK goes to JK.
Oh, index by index or?
Index by index. Index by index. It's very, very strong, okay? This goes to this is the same. Okay? Very, very strong. So it's also a kind of equidistribution, right? It's saying that the permutations, so in the whole, in Sn, this is what happens, right? In Sn, the number of permutations that send anything to anything is kind of the same. So we're saying that they're kind of equidistributed. This is also a type of equidistribution. So these are very, very strong combinatorial structures, okay? And the question is this a graphical design? You can ask, is this a graphical design? On what? On the Sn graph, right? So we need to make a graph with Sn. So these are the vertices of Sn. Let's draw the famous hexagon. Okay, all the permutations. This is Sn, okay, this is S3, for example. I put all the permutations, and then how do I connect it? That's where the trick is, okay? Because this whole theory just works on this much data. But now I need to construct a graph whose graphical designs are going to be this thing, okay? So the nice graphs you can put on these are just Cayley graphs, where you use the conjugacy classes of Sn to connect things. So for example, I could use all transpositions as the edges. So connect two permutations together if they differ by a transposition, okay? So let's do that. Let's use the transposition graph. So my connections are going to be transpositions. This is
Adjacent ones or all?
all transpositions. Yeah, so I don't know, connect it whichever way, I forget how it looks. So connect it, okay? With the transpositions. But you could also use a different conjugacy class. Transpositions form one conjugacy class. You could also, so this will connect things that differ only in two places, right? But you could also connect things that don't have anything in common. That's called the derangement graph. That's another conjugacy class. You can pick any conjugacy class. These are called normal Cayley graphs on Sn, okay? People study this. And then everything is known about them, their eigenvalues, their eigenvectors. We know a lot. It comes from the representation theory of Sn, okay? Now, in this case, it turns out that these T-wise, so what happens is when you write the eigenvectors, okay, we have 2 minutes, I will finish. So what happens is when you write the full eigenbasis, right, then it turns out that the different eigenspaces are going to be basically refined by the partitions of n, okay? Eigenspaces don't correspond to partitions of n, but bunch of partitions will club together to give you an eigenspace, okay? So you can like form a refinement by partitions. So I take a partition of n, and then here you put basically you look at the representation of the group corresponding to this partition. This is a bunch of matrices. You pull out its ij entry from all those matrices, make them into a row and so on. So people know what this is, okay? But turns out that what this is if you average, so this is a design that can average all the eigenvectors, so eigenvectors corresponding to partitions P of n, where what? Where I think the first part, something about the first part, Let me just check quickly so I say the right thing. So I'm looking at T-wise permutations. So the first part of the partition is at least n minus T. This is what you need. Okay? So this sadly is not Laplacian order or reverse Laplacian order or anything that we understand. Okay? So this is just a result. This result is actually proven in this paper of Kuperberg, etc. They're not interested in designs, but they actually prove everything that's needed to prove this result. Okay? So you organize the partitions so that the first part is at least n minus T, and all those eigenspaces will be averaged. Good? So open problem is what are the designs that come from Laplacian order? Is there some nice combinatorics to those permutations? We don't know. So I'm saying that this thing, making the first part greater equal to n minus T, this is not Laplacian order or reverse Laplacian order or anything that makes sense for us. Okay, so so what happens is,
How do you order them within each set? So once you know.
so remember that each partition is living inside an eigenspace. So a partition doesn't cut across an eigenspace. So what happens is every partition, so the eigenspaces could be maybe this is, so let's say in white I have the partitions, the different partitions, and then the eigenspaces, this will be one eigenspace. Then it could be that these two together is another eigenspace. Okay, and so on. So the partitions refine eigenspaces. So if I just say I want the first part to be something, then you may be forced to just take this much. You may cut through an eigenspace, right? Because I'm only allowing the partition, something on partitions. But partitions and eigenspaces of Laplacians don't exactly work nicely. But
This is all transpositions, not.
yeah, exactly. So I think there are many nice questions about Sn for those who like combinatorics. Like if you go in Laplacian order, if I want to average the first T eigenspaces in Laplacian order, you'll get a bunch of permutations as the answer. What are they? Like, do they have some nice structure? They're not T-wise. They're sometimes T-wise, but they have usually some extra structure, right? Because they are also, the design will also average these guys. What does that mean? They'll average all these extra eigenvectors. So that means it's some sub-collection of T-wise. But I think there is some combinatorics. So for those who like permutations and so on, this is a question that would be interesting. So a point was to argue that nice combinatorial structures are naturally graphical designs. And therefore you can say, graphical designs are kind of a very general thing, right? They work for every graph. They work for, there's nothing going on. Whereas orthogonal arrays, all these other kinds of things, there's also these Delsart designs. The whole Delsart thesis is about designs. They work for something called association schemes. They're like super structured. But here we have this sort of, okay, everybody is welcome kind of situation. But what do they capture? And they seem to be capturing nice things in nice graphs. All right, now I will stop. Thank you. And I should thank you for being in class, for asking questions and being engaged. It's a privilege. Yeah. Okay. Lots of open problems. So the students all have access to the open problems I wrote down, but I said a few more now. That's not in that list. If anybody else wants the list, happy to share it.